Suppose we want to use some sort of linear approximation to estimate the value of the cube root of 7.7. This section introduces two main ways of doing that. One is by constructing a function that is referred to as a linearization, and the other is by using differentials. I will work through both of these in this video. No matter which technique we use, we will need to identify an appropriate function and take its derivative. So let's look at this. We see this is a fairly simple function. We see we're taking a cube root of a number. So this obviously suggests a function, let's call it f of x. You can give it whatever name you want. Let's suppose we have the function f of x equals the cube root of x. And again, either technique will require its derivative. So let's compute f prime of x. Of course, you may find it easier to explicitly write f in exponent notation, that is x to the 1/3 power. So then f prime is 1/3 of x to the, subtracting 1 from this, we have negative 2/3 power. So there we have f and f prime. And again, we need to do that with whichever technique we use. For the first technique, which is to create a linearization, as this problem says here, use an appropriate linearization, that refers to constructing a linear function which approximates the function in question near a particular point. So we need to know what point to choose, right? So we'll look at this and we'll think about a value near 7.7 that we can easily take a cube root of. Well, the closest perfect cube is 8, so let's think about that. F of 8, the cube root of 8, is equal to 2. So this gives us the xy pair 8, 2. In the language of the linearization function in the textbook, we would identify a equals 8, and then compute your f of a and f prime of a, so that we have both of those. Actually, let's go ahead and do that. So we found f of a, that is 2. F prime of a, f prime of 8 in this case, that is 1/3 times 8 to the negative 2/3 power. Let's go ahead and take the cube root first, so that is 2, so we have a 2 to the negative 2nd. That's a 1/4 times a 3rd gives us 1/12. So our f prime of 8 is 1/12. At this point, you can plug all of those things into the formula given in the textbook, or if you don't feel like memorizing that formula, because I certainly don't, you can think of the slope-intercept form of a line. Y minus y naught is equal to the slope m times x minus x naught, which of course is just a rearrangement of the slope formula, right? If you divide x minus x naught to the other side, you have change in y over change in x, that's just slope. Our y value here is the linearization L of x. Y naught is the function value. F of 8 is equal to 2, so let's add that to the other side. So we have 2 plus, m of course is a slope, that is our derivative. We computed that to be 1/12. And we have x minus the x value in question, that was 8, is where we wanted to approximate this, right? So we have all of those pieces. This then would be the linearization, if you wanted to construct that explicitly. But again, as I said, you don't even have to use this notation really. If you're working on a problem on your own, just constructing the tangent line through whatever means seems appropriate is probably the best way to go. For computational purposes, I would not recommend multiplying this out and simplifying unless you're trying to get something to write in simplest form. If you're asked for a linearization and that's your final answer, then you want to simplify it, hey, feel free. But if you're trying to just compute a linear approximation, you might find it easier to leave it in this form, as we'll see in a moment here. This allows us, that this function here describes the linearization, the linear approximation for any x value we choose. the closer we are to 8, the better we expect the approximation to be. If we stray too far from that, it will probably not work out as well. So let's see what happens if we try to approximate the cube root of 7.7. So in this case, we want x to be 7.7. So we want to compute L of 7.7. We have 2 plus 1/12 times. Now 7.7 minus 8 leaves us, that looks like a negative 0.3, right? And now you might see part of the reason why it's useful to leave it in this form, because now we get something that's a little bit simpler as we multiply by the appropriate fraction. So let's go ahead and start simplifying this a bit. This is 0.3 over 12. And if we divide 3 out of both of those, we have 0.1 divided by 4. That is 2 minus 1/4 of a tenth. That looks like it's going to become a 0.25. So if we take 2 minus that, we'll be left with 1.975, if I'm doing the mental math correctly. Let me check my notes here, and yes, there we go. So we get 1.975 as the approximate value of the cube root of, let me write that down, the cube root of 7.7 is approximately equal to 1.975. Okay. Now you might ask the question, well, how good is this? Is this even worth doing? So let's compare to a more precise value, not using the linearization, but using a computer or calculator to work that out. And there we get something like I'm consulting my notes, 97468, if I've copied that correctly. Which you see is pretty close, right? There's a non-trivial amount of error here, so you don't always want to resort to linear approximations. It depends on what you're doing. But for many purposes, this is sufficient. And it is less computationally intensive than the process of taking a cube root in general, which may matter if we are computing a lot of these. So that was the method with linearizations. You can just use the formula or ignore the formula and just build up an equation of the tangent line, and then compute at whatever nearby values you wish. Let's also take a look at this with differentials. Now, again, we still need to identify our function f of x. You don't necessarily have to call it f, you could call it y if you prefer. You could make this a variable instead. That'll fit better into some of the other things that we'll be doing, but let's go ahead and have that. And we'll need to compute the derivative at some point, so I'll go ahead and do this just as we did before, 1/3 x to the negative 2/3. Now the idea of differentials, this is based on the fact that, remember, one of the other ways of writing a derivative, f prime of x, we could use Leibniz notation, which was dy divided by dx. Leibniz was one of the independent developers of calculus along with Newton. The prime notation came after Leibniz and Newton developed their calculus. It didn't exist at the time. Leibniz wrote things like dy divided by dx. And as I understand it, he thought of these dy and dx as differentials, as being very tiny quantities. We might almost say infinitesimal, very, very small quantities. And their ratio, what happened to their ratio in the limiting cases they approached 0, is what we understand to be a derivative. Now, a century or two later, people like Cauchy and Weierstrass worked out how to describe derivatives much more rigorously in terms of limits with epsilon delta definitions. And in that context, we can define what a differential is after we have our definition of f prime, like we got at the end of last chapter. if you imagine multiplying the dx to the other side, we can define the differential dy, if y is a function of x, as being f prime of x dx. So our textbook, like many textbooks, takes this to be the definition of what a differential is. A differential of a dependent variable is the derivative of that thing times the differential of the independent variable. Excuse me. And a differential of an independent variable is left somewhat undefined, but we can think of these as being very small quantities, and we don't really want to add or subtract with isolated terms of these, but we can think of multiplying and dividing by these and the relationships that this gives us through derivatives. So, taking this particular example, if we let y equal f of x, the differential dy would be the derivative of that, 1/3 x to the negative 2/3 dx. This is important. We don't want to write that a differential equals an expression by itself. Any differential should always equal a scaled version of another differential. If you have a differential on the left, you should have a differential on the right, because these aren't ordinary real number quantities. dy, outside the context of what we're about to do here, dy doesn't have a lot of meaning on its own except relative to another differential like dx. So we should have a differential on both sides when we work with those. Also, we do think of this as being like multiplication. So if you have, if you take a derivative and that derivative is a sum of two distinct quantities, and you want that to be a differential, you would need to group them together somehow so that the whole thing is multiplied by dx, right? You don't want to write like u plus v dx with no parentheses. That wouldn't make much sense. Similarly, if you have maybe something like this, 1 over u times dx, you might write that as dx over u, right? Again, we think of these quantities like they're being multiplied. And this even works out really well, because if we were to suppose we thought of y and x as depending on some other variable t, if you take the differential dt and you were to divide that on both sides, so you have dy divided by dt is equal to that stuff times dx divided by dt. Well, now dy by dt and dx by dt are derivatives, and what we've just written here is a chain rule. If y depends on x, which depends on t, this would be an expression of a chain rule. So there's a lot that we can do with these differentials and their relationships to derivatives. Let's back that back out because we don't have a t here. I just went off on a little side tangent about differentials and how they work. But in this particular problem, it's a bit more constrained. Let's step back to what we were doing. We want to estimate the value of the cube root of 7.7. The example said linearization. I already did that with linearization. Let's use differentials for a different approach to linear approximations. We let y be the cube root of x. So then dy is 1/3 x to the negative 2/3 dx. Okay. We do need to still identify a nearby value like I talked about. Again, we look at the 7.7, we say, okay, well, this is close to 8, and we can take the cube root of 8, so let's work that out. So if x is equal to 8, dy is equal to, and just like I worked out last time, we can figure out that this is 1/12 dx. Right? So we have here that at the point when x equals 8, the differential dy is 1/12 of dx. We want to compute this value f of 7.7. Okay. And actually, before we do that, let's say this. In general, if we want to compute a value of f of x plus delta x, so we have an x value, and then we have a small change, a delta x there, that will be whatever f of x is plus the appropriate change in y, delta y, however much that changes from one point to the next. And the idea of what we're doing with differentials is that we associate delta x with dx, and we say that, well, if dx is small enough, then delta y should be close to dy. This is the change we would estimate based on just taking the derivative. Here we have dy as 1/12 of dx. This describes the tangent line, the linear approximation. This is saying that at this moment when x equals 8, y is changing at about 1/12 the rate that x does. In other words, at 1/12 is the slope of the tangent line. And of course, dy, we just worked out here that dy there is the f prime of x dx. I'm writing this in general, so let's look at this more precisely in the particular problem that we have. We want f of 7.7. 7.7 is 8 minus 0.3, right? So this should be approximately equal to f of 8 plus that appropriate differential dy, which is 1/12 times dx. I'm using this up here. dy is 1/12 dx. So we have 1/12. This negative 0.3 is the dx, right? And the rest of this works out just like we did before. F of 8 is 2. We get minus, taking a 1/12 of that, we have a quarter of 0.1, giving us that. I'm skipping some of the steps that I worked through earlier in the video. It all works out the same, and we get the same result at the end. Can't have multiple. There we go. That's what happens when I talk and write at the same time. Now this is one way of organizing this. You might find it easier to instead say, so this is going through kind of the theoretical approach of what these functions mean. Let's back this up a little bit. You might find it easier to say, okay, dy equals 1/12 dx. So then say, okay, well, dx is negative 0.3. So in this particular case, dy is equal to that, we have 1/12 of negative 0.3. So we work out what dy is. And now we take y plus dy. So that is 2 plus the dy. And work it out that way. This is probably a much more compact approach. Again, the stuff that I wrote out here is not what you would normally do when you're solving the problem. This is just trying to show how the differentials dx and dy are roughly analogous to the change values delta x and delta y. But if we're using differentials, we probably want to keep the bookkeeping as simple as possible, compute things as we go. We don't even need to write out an explicit function f of x. We could just write y equals the cube root of x. So then dy is its derivative 1/3 x to the negative 2/3 dx. We figure out that in this problem we want x to equal 8. So that tells us that dy is 1/12 dx. Dx is negative 0.3. So we figure out what dy is. Y plus dy, work those out, simplify there. So you just have these small little packages here. If you take this approach, it is more important than normal to make sure that everything is very clearly labeled because we have a lot of different quantities floating around, right? We have y as a function of x. We have a particular x value we're looking at. We have the differential dy related to x and dx. We choose a particular dx value, then we compute the dy value, right? There's all these individual quantities that we need to label and then combine. But some people find that a much easier way to work with these sort of linear approximations. So if you like that, feel free to use it.